So if you have a circuit with two light bulbs as shown, a 60 watt and a 100 watt light bulb, which bulb will be brighter? This is often a bit of a tricky question for students that are working through circuits for the first time. So let's work this through, not just conceptually, but also doing the math. So first, let's just recall some of the tools we need. Principally, we're going to need Ohm's law, which is our V is equal to IR. And we're also going to want to look at the power. And the power is going to be V squared over R, or equivalently I squared R. Okay, so these are our key tools. Okay. So one thing to recognize is that what does this number even mean? 160 watts. Well, it's a power rating. So, but it's under an assumption. So the light bulb power rating is for standard 120 volts. I was going to say standard 120 volts. And so, I've written 120 volts in this circuit. But that's what it means when you just see it labeled 60 watts. Now, that assumes essentially this scenario where you just hook up the light bulb and it's hooked up to a simple circuit where you've got 120 volts. That's what it's assuming. It is not assuming anything more complicated. And so there are some implications here. And we're going to take a look at that. What is it that doesn't change depending on the circuit you are placing this device into? Because when we look at power, it depends on things that can change. It depends on resistance, which doesn't change. It also depends on current and the potential drop. And in particular, we're going to be looking at how the current in the circuit can change due to what else is there and what that does to the power and the amount of light that is going to be emitted by the light bulb. So let's first say, well, let's find the resistance. Of each bulb and we're going to do that because this doesn't change. This quantity is the result of, it's a characteristic of what it's made of. Remember we talked a little bit about resistivity and the shape of the conductive material, and that's what's telling you the resistance. So it doesn't matter what circuit we put into, the resistance is a consequence of character of the material. So let's do that. So I've labeled the light bulbs 1 and 2. So resistance 1 is, well, we can put that as V squared over P, because we can assume this scenario here, which is what the rating is for. And in this scenario, we've got a voltage of 120 volts, and then that's going to be over this 60 watts. And so from that we get 240 ohms. Not a very good omega. I can do better. Okay, so then we can do the same for the second light bulb and find the resistance. And so that again is V squared over P, and 120 volts squared. But this time it's going to be over 100 watts. Okay, so that gives us 144 ohms. Okay, so now we know what the resistance is. Now we can now find the current when we hook this light bulb up to the circuit alone. So, and because we're just solving everything. What's the current? And that's when the bulb is alone. Well, we can solve that by applying our Ohm's law. So the current through that first light bulb is V over R, and we know that V is 120 volts, and we now know that the R is, and we'll just make that very clear, that's the first one, 240 ohms, and so we have 0.5 amps of current. And then we do this again for the second light bulb, and V over R2, and so we have 120 volts over 144 ohms, and we get a current of 0.83 amps. If we want to be consistent in our sig digs, we could say this. Okay, so let's just step back and ask ourselves, does this make sense right now? The current through the second one, the second bulb, which is our 100 watt bulb, is larger. Well, let's think about what that means for the power. And just note that, if you insert these values of current and resistance into the power equation, you get the power of the first one is equal to 60 watts, and the power of the second bulb is equal to 100 watts. Okay, that makes sense because that was the assumption that we made when calculating the resistance here. And it's not really an assumption, it's based on the knowledge of this is how power ratings for bulbs work. But that shows us that we have more current and more power flowing through that 100 watt bulb when it's on its own connected to 120 volts, compared to the case where we have the 60 watt bulb connected to that same power supply. And that's why the 100 watt bulb is brighter under those same circumstances. However, let's back up a moment. What changes when both bulbs are in series? What changes when both bulbs are in series? Well, what changes is the circuit overall is going to have an equivalent resistance. We could redraw we we could redraw this series circuit as having just one resistor, and that one resistor is going to have some Req, and that's going to be equal to the sum of the first and the second bulb. And so let's take a look at what that value is and how that changes the current and the power output by the bulbs. Okay, so Req is now going to be R1 plus R2, and that's equal to 384 ohms. So we worked this out. There's 240 plus 144. So that's 384. Okay, so we've got now a current that we can calculate that's going through this circuit. That's V over EQ, and that current is 120 volts over 384 ohms, and that's 0 point, moment of truth here, 31 amps. How does that compare to the current flowing through the circuit when we had only the one bulb? 0.31 amps is less than both of those cases. Okay, that's very interesting. So now that we have the current, let's find the power. Well, the power from the first light bulb, we'll say, is I squared R1, and that's 24 watts. And the power from the second bulb, again, I squared R2, and that's 14 watts. So there's our difference. With this current, we actually have, and this is just to make a very clear note of it, our first one, this is our 60 watt bulb, and this is our 100 watt bulb. And we can also calculate the voltage drop. So V1 is going to be equal to IR1, and that's 75 volts for the first bulb, and the V2 is equal to IR2, and that is going to be equal to 45 volts. Which makes sense. We've got less power going through the second one, so we've got a smaller voltage drop. And then note here that V1 plus V2 is equal to 120 volts, which we expect because we are going to have a gain of 120 volts from the power supply, and then we drop a total of 120 volts across the two devices. And so that is our analysis of the entire circuit. Understanding now that the rating that we see on a light bulb is assuming that the light bulb's on its own with a 120 volt supply, and as we change the circuit, we change the amount of current that's flowing, and that changes the amount of power and the voltage drop across those devices. And so, in fact, the 60 watt bulb is going to be brighter. So, what about the case where we were to put these bulbs, instead of in series, we put them in parallel? So now let's hook up the 60 watt bulb, still number 1, and the 100 watt bulb, number 2, in parallel with 120 volts. Okay, well, first of all, we aren't going to do all the work over again. We're going to port over information from the previous and say, well, we know from above that we have the resistance values. And that's the starting point here. I mean, we're given the power under a specific circumstance from which we calculate these resistance values, because these don't change. So we've got a resistance 1 of 240 ohms. And we've got an R2 of 144 ohms. Okay, we also know that V1 is equal to V2, which is equal to V, and that is 120 volts, because they're in parallel. Okay, so now we can say, well, what changes when you put things into parallel? Well, we've got a couple of things that we can do. We can look at the equivalent resistance, for example, and use that to calculate the current. Or we can also calculate the current from the potential difference and resistance. So we've got some choices to make here. Let's just note that we've got two ways to go. I'm gonna start by saying I'm gonna find the current. So current 1 is going to be equal to our V, because V1 is equal to V2 equal to V. So just V over R1, because we know that. And so that's 120 volts over 240 ohms. And so that's 0.5 amps. And I2 is going to be V over R2, so 120 volts over 144 ohms equal to 0.83 amps. Okay, now we know that this I1 that we calculated, well, that is the current that, so we've got current that's going to flow like this, and then we're going to have some current I2 here, and we're going to have some current I1 here. And so the total current in the circuit is going to have to be equal to 1 plus 2. So our I is 1 plus 2. We call it I total if we wanted to. And that is 1.3 amps. Okay. So from there, we could go on and find the power. That's enough information to find the power. So we'll go power through 1 is equal to I1 squared R1, or 0.5 amps squared times 240 ohms. And so power 1 is 60 watts. And we could do power 2 is equal to And again, it's I squared R2. So I2 squared R2. And that's going to be equal to 0.83 amps squared times 144 ohms. And so power 2 is equal to 100 watts. Okay, now let's just remind ourselves that there was an alternative way to go, which was to look at the equivalent resistances. And that would then be connected to the total current as well. So if we had found the current, the total current, which is here, we could also recognize that there's a relationship with our EQ, which is equal to V over I, and this is the total. If we want to make sure this is really clear, that's the total. Okay, and so in that case, we could say, well, this is 120 volts, and that's 1.3 amps, and so we get an REQ of the circuit of 90 ohms. Now, the other way to do this, or what we could have done was 1 over REQ is equal to 1 over R1 plus 1 over R2. And if we did that, we'd work it through and have 1 over 240 ohms plus 1 over 144 ohms. And we end up seeing that we have 90 ohms. And then from that 90 ohms, if we had done that first, we could have then got the total current. So there were multiple paths here, because everything's nicely connected. So after having done this for both, which type of circuit? Series or parallel is more useful for lights? Well, one might argue persuasively that parallel circuits are more useful because they're able to provide us with this power that's aligned with the ratings that are labeled, and so we get more power, we get more light. So that's good, right? Are there any trade-offs here? There is a trade-off, and give a moment to think about what that trade-off is. Is there a danger here? So keep in mind that what did we do to get this power? Well, we lowered the overall resistance, and that gave us higher current. And that higher current enabled us to have that higher power. This carries risk. Could you do this ad infinitum? Could you just keep adding more and more parallel lights? Eventually, you're going to have such high current, such low resistance, that the current may actually overwhelm the wires and the materials that are being used, and the likely outcome there is a fire or things melting. That's probably not what we want. So there is this balance here that we don't just get power for nothing. You have wires that are rated to handle a specific maximum amount of current, and it is very unwise to exceed that. So here's our analysis of these classic which bulb is brighter questions. Hopefully it was illuminating.